I think it's this one. So, is it recording now?
No, not yet.
The recording from Zoom and the one in the class is different. We cannot detect this recording.
Yeah. I think you need help from ICTP.
Yeah, but there is no time. So, if I go, I think I press the right. So otherwise we stop and then I check because I don't remember. I think it was this right button. Okay. So just wait for a second. I will ask. Okay. I'm just asking to the secretary to know if I'm pressing the right.
Sleeping.
Don't say that.
Why? It's not recorded.
And I think the staff is also not here. If not, we will be able to answer the problems.
Oh. But we don't know what's happened, right?
ICTP Diploma, so we should start with
Maybe he left for something important.
Yeah.
he's taking a break because it's continuous.
Hey everyone, why suddenly Professor talk about the level, lambda level, energy lambda something?
Lambda? Oh, you mean EBS?
Yeah.
I don't know that part. I was asleep.
I think this is correct. Okay. So what I press is correct, but yes, it's correct. Okay. Yeah, there are instructions here. Okay. So this is the wave function. Okay. The density matrix is an object which is needed to describe a quantum system in situation where quantum wave function cannot be used. So I just repeat the same explanation as last time, but first let me say that if you have a system which is described by a density matrix, by a wave function, then as well you can describe it as using density matrix, because instead of psi you will introduce a projector which is psi. Instead of the Schrödinger equation, you have that this rho is equal to minus I, h bar. Today I just put h bar. The commutator of rho with the Hamiltonian, and the average value of any physical observable is just the trace of O times rho. Now, I just remind you that rho is an operator, okay? It's a projection. However, since is describing a quantum state, then in the Schrödinger picture it evolves in time. I just remind you that the Schrödinger picture wave function evolves and operators do not depend on time. In the Heisenberg it's the other way around. Here the fact that rho is an operator is the only operator which evolves in the Schrödinger picture. Now in this particular case, so when rho is given by this projector, which I remind you last time we call it pure state. Using rho or using psi is totally identical. However, there are situations in which wave function cannot be used. Now, let me ask you one question. So, do you know what is quantum interference? May you explain? So, can you give me an example of quantum interference state? Hello? Are you there?
Yes, but I don't know.
P is not in the mid-change.
So I propose the following. Can you switch on the videos? Because I see that you are muted. I do not see your face. So I don't know if you are, is it complicated? I mean, I think it would be good. It's better that, okay, if you can do it. Very good. So, what is quantum interference? Huh? Oh. So what is the, so tell me. Do you have an idea? So if I tell you, if I use the word quantum interference, do you understand what I'm saying or not?
It's related to the superposition of wave function.
Very good. So let me make the following example. So suppose that I have a system which can be in the state psi 0 and it can be in the state psi 1. Okay? What? And then I want to know what is the probability that I find it in position x. What should I compute? So for instance, supposing that the wave function is psi 0. What is the probability that the system in the state psi 0 is found in the position x? What should I compute?
Take the inner product of
Yeah?
x and psi.
Very good. So I just compute the probability to be in x is just x times psi 0 squared. Okay? In the same way, if, and this I call it P0. Okay? In the same way, if I want to compute P1, I just compute the x psi 0 squared. Now, suppose that I create a superposition of
Sorry?
yes,
In the second case, I think x psi 1.
psi 1, right? Is this what you meant?
Yes.
Very good. Now, suppose that I consider a quantum state which is given by a superposition of psi 0 and psi 1, okay? Such that alpha squared plus beta squared is equal to 1. Then, what is the probability to be in phi? Okay, I just call it P phi of x. Tell me the result. So, tell me. So I have to take the square, the modulus square of this. Okay? So I guess it's alpha squared P0 x. Okay?
Yeah, plus beta square P1x.
Then
And some clusters if they're not orthogonal.
huh?
Are they orthogonal, Professor?
No, they're not orthogonal.
Then we have clusters.
Right. So we have something which is related to something, I don't want to write, but it's something like x psi 0, psi 1 x, okay, is related to the real part, okay? And then we have alpha star beta, and probably is a factor 2, okay? So you see that because of superposition principle, the probability is not given by the sum of the probabilities, but there is also some interference term. Okay? Now let me consider a different situation.
Sorry. What did you write on the last term? I cannot see, too small.
Very good. You have to do it yourself.
Oh.
That's why I did not write it. Actually, I will remove it because this is something you should be able to do it by now. Okay?
Yeah, of course. I mean, just cannot see.
I put dots. Okay? But these dots are important because these are related to what you say is related to quantum interference. Okay? So these terms here, so you see, I do it, okay? So I have to do it alpha x psi 0 plus beta x psi 1 modulus squared, okay? So this is equal to these two terms, alpha squared plus p0 plus beta squared p1, then I get alpha beta star x psi 0 psi 1 x, okay, plus complex conjugate. Okay? So this term here is an interference term in the sense that the probability can be larger than or smaller. I can just create like waves. Okay, I can create or destroy. Okay. Sorry, I can have constructive or destructive interference. Now, but I don't want to discuss about this. What I want to discuss is about a different situation. Okay. Now, I just made this example also last time. So just consider the following. I tell you, look, with probability, I do an experiment in which with probability P0, I produce the state psi 0, and with probability P1, I produce the state psi 1. Okay? So this is classical probability. Okay, I just generate random numbers and then a fraction P0, I just prepare the state psi 0, and a fraction of times P1, I prepare the state psi 1. Now, what is the probability that, so suppose that if P0 is 1 and P1 is 0, of course, I mean, I should have Okay? Now, what is the probability that the system is in the state X?
I'm sorry, Professor. It's the last statement again.
Sorry?
Can you please repeat the last sentence again?
Yeah, I want to know what is the probability that the system is in a position X. So you just do an experiment many times, okay? You generate an ensemble of quantum system, but in a fraction P0, you prepare the state psi0. In a fraction of time with probability P1, you prepare the state in psi1. And then I ask the same question as before. So what is the probability that the system is in X? So, but you don't know if you prepare it in psi0 or in psi1. So you solve this problem. I just formulate differently, but you solved this problem last time. So what is the probability to find the system in X?
Is not the problem.
Eh?
The condition, like
Sorry?
ability that we have the condition when we have the state in final.
Yeah? Okay, so give me, I think you gave me the right answer last time. I'm not sure. So what is the right answer?
What is P0?
So I have small p0, there are too many p's. P0 times what?
Scalar product of S.
Yes?
5 and P1 plus P1
Plus?
P1 and scalar.
Okay? So now suppose, just to make a connection to what we wrote 2 seconds before, I call it this. P0 is alpha squared and P1 is beta squared. Okay? So what is the difference of this result from the previous result? So in this case there are no interference, because in this case we just sum up probabilities. In the previous case, where the state was a superposition of two states, there were interference term which came from the cross product. Okay, we just square the amplitude and then, sum the amplitude and then square. Here there are no cross product. Okay? Now, if I ask you, so I just define it like this, okay? But if I ask you, can you explain how, so what is the object to describe the evolution of this quantum state? You cannot assign a wave function to this object, okay? In fact, I just wrote it by hand. I just said, look, if I have this P0, I have this psi 0 with probability 1, I have psi 1. Okay, but I don't have a wave function associated with this ensemble of system. You know that, we have this statistical description in which we have an ensemble of quantum system. Well, however, if I have a density matrix, this is not the problem, because in this case I can introduce rho as P0 psi 0 psi 0 plus P1 psi 1 psi 1. Okay? And then, for instance, if you want to compute the probability. Okay? So what is the probability to find the particle in X? Okay? So what is the rule? Trace of rho. What is rho? And then what is the operator that you should put here? You should put the projection operator in X. Okay? You have to compute the trace of rho times XX. If you do this with the rule I gave you last time, then automatically you see that this is equal to P0 x psi 0 squared plus P1 the right result. So you see that in this case, since the uncertainty was not related to quantum mechanics, but it was just related to classical probabilistic effect, you don't want to, you cannot use quantum wave function, but you have to introduce density matrices. Now, a wave function is a vector in the Hilbert space. We saw that a density matrix is an operator in the Hilbert space. But are all operators allowed? No. There are certain properties that the system, the operators should obey such that they are good density matrices. So they should be Hermitian. They should be positive definite. So if you take any vector phi rho phi should be larger or non-negative, and the trace, so 1, 2, 3, the trace of rho should be equal to 1. Now, if you have these properties, then you can always find the basis. I mean, since it's a Hermitian, you can diagonalize with eigenvalues which are real and non-negative, and you can always find a basis such that you can write in this form. Okay? So that sum over I, Pi, should be equal to 1. Okay? Now, last time we introduced something which we call purity. Purity is the trace of rho squared. The trace of rho squared is equal to 1 only if rho can be written in this form. So all the probabilities are 0 except 1, which is 1, or is smaller than 1. So in this case we call it pure state, and in this other case we call it mixed state. Now with pure state you can use equally well wave function or density matrices. However, with mixed state, only density matrices can be used to describe a quantum system. Now, do you have any question on this, or can I go on?
Yeah, you can go on.
Very good. let's make some examples. So suppose, so did you study the spin up and spin down? Spin 1/2, you know?
Yes.
Very good. So I just consider two states, up and down, okay? So I write the following. Okay, so I wrote 3. Do you see this? So is this a good density matrix? So does this what sorry, I just made sorry, stop. I just made a terrible mistake. So I have to write it better. Okay? Okay. Okay, so the first example, is this a good density matrix? Does it describe the physical state or not?
Yes.
Why?
Because it satisfies all the properties.
Very good. So this is okay. So tell me the second, is it a density matrix or not? Huh? No.
No.
Why? So what is the property that it violates?
Trace or
The trace.
Very good. So this trace is the trace is not 1. Good. So the third one. Yes or no?
No.
You don't know. Because you have to check step by step. Okay? So we don't know. Probably no, because I just invented. Okay? So the probability that I got it right is almost 0. But you cannot say no. Okay? I wanted to cheat you. So what you have to do? So first of all, you just write, for instance, this in a matrix form. Okay? So this is a 2 by 2 matrix. Right? So let me write it. So with 1 and 2 is okay. Okay? So you got it right. So let's see this one.
I think it's quite obvious from the diagonal term. You can see it directly. Because the first diagonal term is 1, the second one is minus square root of 2 over 3, so the trace is not 1.
Okay, so then it's no. Okay, probably is even, so then you're right. This is a very good answer. Okay, so the eigenvalues are let me say, what are you supposed to do? So you have to write down this. So for instance, you just write as a 2 by 2 matrix. So you have square root 2 over 3 plus square root 1 over 3. Okay? Then you have another term which is minus 1. Okay? And then you have a mixture term. No, sorry. This is 1. So sorry. No, I just did it.
Minus.
This is minus. Okay. Sorry. This was even wrong. So I should have I should have written minus here. Okay. So it's plus 1. So your answer was correct, but I made a mistake. Okay. So what I wrote was. Okay, I wanted to consider this case.
2 over 3.
Oh, sorry? I just wanted to consider this case, okay? So I have now a minus here and a minus here.
No, I mean, you have square root of 2 over 3.
Yeah, it's not plus 1, it's square over,
Yes. Yeah. Okay? So, from here you see that so it's not as bad as you said in the sense that it was negative, but in principle you just compute the trace, okay? And then you find the eigenvalues. Now, even if you find that the trace is 1, then you have to be sure that the eigenvalues are both positive. Okay? Let me make one example. So suppose here you get 1/2 and 1/2, and then you get plus I minus I. Okay? I'm just writing a new thing. So the trace is 1. Then you have to verify, so it's an admission. Now you have to verify, so you find the eigenvalues and you have to verify that they are both positive or non-negative. So one eigenvalue can be 0, but then they should not be all non-negative. Okay? Only in that case you can say that this will describe a quantum state associated with a spin 1/2. So we'll come back to this example, so to the case of spin 1/2 in several other occasions, so we'll continue to do exercise on that. Question, can I erase this or you have some, can I cancel? Good.
You are saying that even though you calculated the trace to be 1, you need to make sure that eigenvalue must be non-negative.
Yes.
Describe the eigenstate of quantum system with spin 1/2.
Yes.
And
so for instance, what I want to say is the following. Suppose the following, okay? Just to give you some concrete example. If you put here 3 and here -2, this matrix has trace equal to 1, okay? But in this particular case, one eigenvalue is positive and one eigenvalue is negative. So this particular matrix does not describe. So it is admission, but it does not describe the physical state. So this is not good. Okay? So you have to verify all the properties.
Oh, you're talking about the second property, right? The negative expectation value of the
Yes.
density matrix.
Yes. Because you see that once you write the density matrix, you can diagonalize, and once you diagonalize, you will find that this is equal to sum over I, pi, psi I, and this has the meaning of probabilities, so they cannot be negative. Okay? So, if this is okay, then I will complicate your life in the following way. Now, I'm going to ask you a very difficult question, so concentrate. I keep considering a spin 1/2, so we'll just use up and down as the basis, okay? The eigenstate of the spin along a given axis, the z direction. So if I tell you, look, I'm going to do the following experiment. With probability 1/2, I will prepare the spin up. With probability 1/2, I will prepare the spin down. Can you tell me what is the associated density matrix? Yes, you can tell me. Now, what is it? You should speak louder, otherwise.
Can you tell us again the question?
Yes. So, suppose that I'm in a given lab, okay? And I do some experiment. I don't reveal what is the experiment, but I tell you, look, what I'm going to do is to prepare an ensemble of quantum system with probability 1/2 in the state up and with probability 1/2 in the state down. Are you able to write down the density matrix? Yes.
I think it's just 1/2
So it's 1/2 up plus okay. Now be careful. I told you what was the way I prepared the state and you guessed the density matrix correctly. Now I want to do the reverse process. Okay? So I tell you what is the density matrix and you try to guess how I prepare the state. Okay? Is my statement clear? So it's the opposite. Okay. I just say, okay, here is your density matrix. Can you guess how you prepare the state? So this is the density matrix that you have. Can you guess what was the experiment that I did in the lab?
Is it just taking the components from the expansion of rho?
Okay, so, right, so just look, just give me an answer and see. So the answer can be yes or can be no. If you give me the wrong answer, then I will continue the lecture. So, can you guess how I mounted my apparatus in the lab?
Yes.
Huh? Sorry, I did not hear. Huh?
I said yes, we can.
Okay, and what is your answer?
Yes. 1/2 alpha.
Yeah, so you are tempted to say, well, in your experiment you prepare the system with probability 1/2 in the up state and with probability 1/2 in the down state, right? Okay, just do the following exercise.
Maybe there's a superposition term that cannot be predicted.
Exactly, this is the point. And this is very important. Look, these are difficult questions, so don't worry. So just take those two states, okay? You just take the state A, which is alpha up plus beta e to the I phi, so alpha and beta are real here. And B as alpha up minus beta e to the I phi down. So if you prepare the state rho equal to 1/2 A plus 1/2 B, this turns out, you do the exercise yourself, turns out to be equal to 1/2 up plus 1/2 down. So you have to do it, okay? You just do it. You just take those two states, you write down this, you just do the calculation, and you will find that this is the case. So what are we learning? We are learning something which is very, very important. From what I have here, actually I can write down formally, but it is not really very important at this stage. Actually there are an infinite number of ways to go to get the same density matrix. So if you have a density matrix, this does not correspond to a given preparation setting. Okay? While if I give you a given preparation setting, then you can write down the density matrix. But just by looking at the density matrix, you cannot say, oh, this comes from some given property. Okay? Now, density matrix is something that you already saw. So I'm just using this preparation way because it's simple in my view, but I mean, I think when you study statistical physics, then you saw that a given system is prepared in a state in which it will be in one of the eigenstate of the Hamiltonian with probability given by the Gibbs distribution. This is a particular case which concerns thermodynamics, but it's also another example in which you have also some classical probabilistic content associated with the quantum state. Okay? Now, as I told you before, I want to consider some exercise, some cases related to spin 1/2. So I want to find a way to write down the density matrix for a spin 1/2. So another question, do you know what are the Pauli matrices? So did you study the angular momentum? Yes. Huh?
Yes, we will study that.
Sorry, do you know what are the Pauli matrices? So if I write sigma x is equal 0 minus I, 1, 1, 0. Do you know this? Do you know these matrices?
Yes.
Okay. So, for a spin 1/2, the density matrix is 2 by 2 matrix. Okay? Now, if you know this matrix, you know that if you take sigma x, sigma y, and sigma z together with the identity matrix, they form a basis. So you can write any matrix in any 2 by 2 matrix using this object. So this means that the density matrix for a spin 1/2, so in this case, can always be written as A0 identity plus AX sigma x. So I just put the hat to say these are coefficients, okay? Plus AY sigma y plus AZ sigma z. Huh? Now, as we discussed before, not all the value of the coefficients are allowed, okay, in order to describe the density matrix. Let's see step by step. So first of all, the coefficient should be what? Can be complex or not?
They should be real.
They should be real because we want that the rho is a Hermitian, okay? It should be self-adjoint, so the coefficient should be real. Then, moreover, what is the value of A0?
A0 should be positive.
Yeah, it should be, but any positive or should be some specific number. Just look at this sigma at the sigmas.
Yeah, it should be. Should be we have positive fraction, I think.
Yeah, you're getting closer. Which fraction?
One half.
Very good. Because we want that the trace should be 1, right? So this should be 1/2. Okay? So since I'm just, just to simplify, I just use different coefficients such that here I have, so let me see how I have in the notes. Yeah. Okay, so these are coefficients, so I just introduce the 1/2 for simplicity. Good. So this AX and AY and AZ can be whatever. So I just remind you, sorry, just a moment, that if I write it this way, I just get 1/2, and then I have 1 plus AZ, 1 minus AZ, okay? Then here I have AX plus minus AY, and here I have AX plus AY, okay? I'm just using this parameterization. Now I want to know if this is enough or I need extra constraints.
We need a bit more constraint.
Okay, which come from what?
The condition that the eigenvalues
Very good. So, very good. So we still did not check. I mean, if we just take any value, this is not guaranteed that this is positive definite. So we have to check the eigenvalues. Okay? Now, if you compute it, okay, you just do it. It's not difficult. I give you the result. The result is the following: ax squared plus ay squared plus az squared should be smaller or equal to 1. So I can have just a geometric representation of all the states for a spin 1/2. Just imagine that I have the following. So I have a y, an x, and az. Okay. So I take a sphere. I just take a sphere of radius 1. So this sphere has a name. This is called from a physicist block sphere.
In your matrix, it should be
Sorry, I do not.
element. The matrix element 2, 1. It should be ax plus a1.
This one?
Yes.
It's ax plus ay.
Yeah.
What is the question?
Yeah. Do you wrote it a1 plus a1?
No, ay, no a1, ay.
Yeah. I cannot say.
So I just have ax, ay, az. Okay?
I see.
Professor, you forgot the last square in the AZ.
Very good. Yes.
And also, can I take you back for a minute?
Where?
To the part where you say there are infinite way of number to prepare the same density matrix.
Yeah?
You gave us this these two states of superposition, which is A and B, right?
Yeah.
And then you have alpha and beta.
Yeah.
Is it also happen that alpha squared plus beta squared equal to 1?
It should be, because the state should be normalized, yes.
Oh, so I think I calculated it, and then I think you should reverse the constant of alpha and beta in the B state. I don't know if I'm wrong.
Okay, I can check. I mean, if I make so you are saying that so alpha square plus beta square is 1, so it should disappear, if I remember correctly. But if you show me the calculation, we can easily verify. I mean,
Oh, so maybe. I mean, it's like this. Can you see it?
no, sorry,
Okay.
I don't know.
So,
I
for the first part, you get alpha squared for both spin up, and then beta squared for both spin down. For B, for the B part, I think we should.
Sorry, probably, did I write, because I think the state B should have beta and alpha interchange. Probably I just made a mistake there.
Oh, yeah, so it
Okay.
should be interchanged, right?
Yeah, so in A, alpha should be in up and beta should be in down. And because they should be somewhat orthogonal, and in B you should have beta in up and alpha in down. I don't remember now what I wrote, but if this is a mistake, probably it should be this one. Okay?
Yeah, thank you.
Thank you. Okay, so I was telling about the block sphere. So you see that all the states, the physical state, can be represented here in as points inside the sphere of unit 1. Now we have an extra information, that is the purity. Okay? So you can compute it and you can verify that the purity is related to the radius of the sphere. So on the surface of the sphere, the purity is 1. Inside the sphere, the purity is less than 1. So for this particular case, all the states which are on the block, on the surface of the block sphere, are pure. The mixed state are all those states which are inside the block sphere. Just take the example, the most extreme example is the one in which AX and Y and Z are 0. If they are all 0, you see that the density matrix is just 1/2 the identity. And the purity takes the smallest value, which is 1/4, because you have to take the square of the identity, which is 1/4. So for this case of spin 1/2, you have purity which goes from 1 on the surface of this block sphere to 1/4, which is the center. Okay? Now, let's try to use this example to understand better the meaning of...
Sorry, Professor.
Yeah.
Can you repeat the last sentence about the purity changes to 1/4 of
Yeah,
the
so basically you can do the following. You can just verify that the purity is 1 on the surface of the block sphere, and I will show you in a second, okay? Also this particular case. When you take a state which is not on the surface but inside the sphere, okay, so the radius, this is smaller than 1, the purity is less than 1. So this means that the only, for a spin 1/2, the only states which are pure are those states which are on the surface of the block sphere. Okay? So the most extreme case, the most mixed state is the one in which this, and these are 0. Okay? And this is the case in which the density matrix is just the identity, or is proportional to the identity. And you see, in this case is 1/2 the identity, and the purity is 1/4. Okay? Now, let me consider pure case, the pure states, okay? So, I want to consider those pure states. So in this case, we said that ax squared plus ay squared plus az squared is equal to 1 for pure state. Okay? So since you have this, then you have this condition, you can parameterize this with 2 angles. Okay? It's like, having, you go to polar coordinates, right? If you go to polar coordinates, if you want to characterize a point on the surface of this sphere, you just need 2 angles, right? And you can write like this. Ax is equal to cosine theta, cosine phi. Let me just use the standard notation. Sine theta, ay sine phi, sine theta, and az is equal to cosine theta. So you just use this parameterization. Okay? This automatically includes this constraint, and you can write down the density matrix. In this particular case, the density matrix is nothing else than rho, let's say rho pure, okay? I just call it rho pure is 1/2 1 plus cos theta, 1 minus cos theta, and here you have e to the minus I phi sine theta and e to the I phi sine theta. So I suggest you that you just do the calculation yourself. Now, what is nice, but you know that if you have a pure state, then the density matrix will correspond to, so for pure state, the density matrix should correspond to some wave function, should be the projector of the wave function, okay? Pure. Now, associated to this density matrix, there is a wave function that is the following. side of theta and phi. So, and I just write the two components, okay? Let's say e to the minus I phi over 2 cos theta over 2 up plus e to the I phi over 2 sine theta over 2 down. This is the associated wave function. Now, so basically these theta are just the angles like this. So this theta is this angle, and this is phi, okay? So let's take, for example, theta equals 0 and phi equals 0. So what is the state? For theta equals 0 and phi equals 0, it's just up. So we are at the north pole of the Bloch sphere. And this is the eigenstate of sigma z with the eigenvalue plus 1. If you take phi 0 and theta equal pi, you are here in the south pole. Okay? So you see this angle are not drawn nicely, so I'll just do it here. Okay? It's like you just take one point and you just take this theta and this phi. Okay? So if you take theta phi equals 0 and theta equals pi, then
Professor?
yeah.
Sorry, but I think the diagram you show us in the Bloch sphere is a little should be interchanged between x and y because it's
This one. Let me check. Yeah, just a moment. Yes, you're right. Yeah. Yes.
And also I have a question.
Yeah.
Is it a requirement for the pure state that it will, is it exclusive to the pure state that the wave function or the ax, ay, az can be expressed by theta and phi only, or?
So, the fact, so the answer is yes. For this guy, for spin 1/2, of course. Huh? And it comes from the fact that if you compute the purity, okay, so what you just take this expression here, okay, and you just do the rho squared and you compute the trace, okay? Then if you do this, then you can verify, using the property of the Pauli matrices, that the pure states are the one on the surface. So if one state is on the surface of the Bloch sphere, is pure, if it's inside, is mixed. Okay? So this means that all and only the pure state are the ones such that the sum of a squared plus base ax squared plus ay squared plus az squared should be equal to 1. Okay? And if you have such a condition, then you can use two angles to represent the state. Okay?
Actually, I still don't get the connection. Is it because of the constraint or?
Yes, exactly. So you have, it's like, so if you have a sphere, so if you want to write down the surface of this sphere, then you can solve the surface of this sphere by introducing two angles. So is it okay?
Oh yes, because the r is constant on the
Yeah, so the r is Okay, so it's like taking the polar coordinates only for r equal 1. Okay?
Yes.
Now just take pi over 2 and phi equals 0. Sorry, I think this is correct. Sorry, no. Because you see, when phi is 0, then AX is... so I think this should be AX and AY, okay? So I think what is wrong is the direction. So this should point in the opposite direction, okay? Because you see, when phi, so when phi is pi over 2, AY is plus 1, so the direction is this one, okay? Okay, so who asked me the question about
Me. I think it should be the right hand coordinate, right? The one we use.
this one? So you see that, for instance, when theta is pi over 2 and cos phi, so when phi is 0, this is AX, okay? So this should be AX.
Yes.
Okay?
But you can actually move the function if you want.
Yeah, you can change it. I mean, it's not an issue. I mean, you can do whatever you want. I mean, the important thing is to parameterize this on the... Okay? So, something which I wanted to point out is, for instance, the case in which phi is 0, and then you take pi, so theta equal pi over 4. Here, if you take phi equals 0 and theta equal pi over 4, the state will be up plus down, 1 over the square root of 2. You see, but up plus down is an eigenstate of spin of sigma x with eigenvalue plus 1. The same is true for if you take the opposite, you take phi over pi, then you will verify that this is equal to an eigenvalue of sigma x with eigenvalue, it's an eigenstate of sigma x with eigenvalue minus 1. And if you take the angles to move along the y-axis, you will find that the states are described eigenstate of sigma y. Now, you can verify, actually you should verify that for the pure state, any point on the sphere is nothing else than the eigenvalue of the spin along the unit vector n. So if you have a unit vector n characterized by the angle and phi, this state will be an eigenstate of this operator. So how do you do it? Well, you just take this, you take this operator with n expressed in this form, and by using the properties of the Pauli matrices, you'll verify it. Okay? Why I'm saying this? I'm saying this because then the meaning of pure mixed state in this particular case acquires a nice geometrical interpretation.
The m dot sigma is the pure state density matrix.
No, sorry. So I explain again. So I just take a unit vector n, okay? This is a unit vector.
Yes.
And then I define, so this unit vector is such that you have, I define nx sigma x plus ny sigma y plus nz sigma z. Okay? And this is a unit vector in the sense that, okay, I just put, just to be clear that this is a vector. N should be equal to 1. This is a vector, okay? With length 1. So I define this operator. Okay? Actually, I just make it even more clear. This is the operator and okay? Okay?
Yes.
Now, if I take the state psi, theta, and phi, will be an eigenstate of n dot sigma, where n is directed along is characterized by the angles theta and phi. Okay?
Yes.
Now, so it's like writing in this way. Instead of theta and phi, I just put the vector n. This raw pure n is just an eigenstate of this operator. In the same way, so if I have the up is an eigenstate of sigma z, okay? Because up is characterized by theta equals 0 and phi equals 0, okay? Or theta equals pi. If I take theta equals 0 or pi, this is 0, this is 0, and this is nothing else than sigma z, okay? So I'm saying when theta is 0 or pi, this state is an eigenstate of sigma z. If theta and phi are generic, what is the eigenstate? The eigenstate is, what is the operator of which this is an eigenstate? Is this n dot sigma. Okay? Now, suppose that I have now a generic state rho. So not pure, it can be mixed, okay? Which is characterized by ax and y and z with the constraint I gave you before. And I want to compute n dot sigma. Okay? So what is the rule? I have to do the trace of rho times n dot sigma. Okay? So again, this is something you have to do yourself. You just do it, and then you will find that this is equal to n, these are numbers, dot a. Now, let's analyze this result, because this has some interest. Let's consider first a pure state, okay? If you have a pure state, when you choose A's parallel to N, the probability to measure this will be 1. Because you are in a given eigenstate. Okay? And you will get, the result is +1 or -1 depending on if it's positive, the eigenvalue is positive or negative. Okay? If you move from this, then the probability will change. But there will be a case in which you get exactly 1. Now, if on the opposite, consider the maximally mixed state. So, when the density matrix is 1/2, the identity. When the density matrix is 1/2 the identity, you see that this will be 0. In any direction. So let's try to give some geometric interpretation. If you have a pure state, then the average value of the magnetization will be picked in the direction of which points out in the corresponding eigenstates, and then changes. We'll have some angular distribution. Okay? You can construct also the probability distribution, which will be 1 if you are pointing in the right direction, or decreases, goes to 1/2 if you are orthogonal. Okay? If you are in the completely mixed case, then the system is totally isotropic in this block sphere. So there is no preferred direction. So what you get is the average value of the spin, any direction you take, will be 0. Because you will have the same probability to get plus or minus eigenvalue with any direction you choose. Okay? If you are in between, the system will tell you a little bit about the direction where the density matrix is pointing, but it will not be as definite as in the pure state. So this should convey also the explanation, the picture that the purity is associated with the degree of polarization, of spin polarization of a given state. The more pure it is, or the less mixed it is, the more polarized state you have. I want to do the last thing for today. That is the following. So far, I consider the need to introduce density matrices only because, well, I had some classical uncertainty present in my experiment or in my theory. I will show you now that density matrices, mixed states, will appear also in cases in which you have the initial state, it's a pure state. Okay? So I will now consider a system which is formed by a bipartite system, a quantum state which is bipartite. So you have a subsystem A in which you have certain bases, alpha, and subsystem B characterized by subsystem, by basis beta. So basically you may have two spin 1/2, okay? Or whatever, two harmonic oscillator, two particle, whatever you want, okay? Now, the most generic state you can write down in this case is the sum over alpha and beta of coefficients A, alpha, and beta, and then you have alpha tensor product beta, right? Huh? Okay or not? Okay? You are muted, so I don't know if it's okay or not.
Yeah.
Okay. So look, since I'm lazy, I don't want to keep writing this tensor product. I will write this way. Okay, alpha comma beta. But don't, I mean, it's the same. So this is a wave function. So this means that the state is pure. Okay, because it's described by a wave function. Now, what I want to do is the following. Suppose that I have only access to physical observable associated with the system A. Okay? I want to compute the average value of A, or A, which means that basically I should consider the identity over B, because I want to compute the average value of A. Well, I just take the state, I just substitute, and the result is immediate. I just get sum over alpha and alpha prime, sum over beta, A star of alpha prime beta, A alpha beta, alpha prime or A alpha. This is the result. Okay, there is nothing mysterious. You have to put the sandwich between O and the states, and you compute this. But there is something very interesting. That is the following. This you can write down as the trace of rho A times OA, where rho A is just equal to the, don't worry, I will explain what I mean. The trace over the subsystem B is called the reduced density matrix of the state psi, which means the following. So you have to take the state psi, so rho A. Psi is equal to sum over alpha beta, alpha prime, beta prime of A star alpha beta alpha prime, beta prime, and then alpha, beta, alpha prime, beta prime. Okay, this is just the definition. And then you have to take the partial trace only on the subsystem beta, which means that you have to do the following operation. Trace over B of rho, or sorry, psi is equal to sum over beta bar of the sum over alpha, beta, alpha prime, beta prime, of alpha A star, alpha, beta, A, alpha prime, beta prime, and then I have alpha, alpha prime, and then here I have beta bar, beta, beta prime, beta bar. Okay? But these are two delta functions, okay? This I can write as the sum over,
Professor,
yes?
why is the density of A is equal to the trace on the subsystem B?
This is the definition. So the trace, you have to take the sum of the diagonal components, okay? The partial trace is defined in this way. So it's called partial trace, so I went a bit too fast. So I have to take the trace only to the indices of the system B. Okay? So I just have to sum. So suppose that you have a matrix A, alpha, alpha prime, beta, beta prime. Okay? So the trace over B, the partial trace over the subsystem B means that I have to sum over A, alpha, alpha prime, beta, beta, and I have to sum over beta. Okay?
But why is some?
What?
But why? I see. Is that?
No, this you have.
What is that?
What?
B prime and B. Beta prime and beta.
So you see that I have to take the trace, okay, over the index beta. So I just multiply this by beta bar and then sum over beta bar, okay? This is a delta function, delta beta bar beta, and this delta beta bar beta prime. And what I get is some alpha prime alpha beta, I just call it beta, okay? A star alpha beta, A alpha prime beta of alpha alpha. So this is row A. This is just take it as a definition, okay? Now it comes the important physical thing. If you take this density, this reduced state, you can verify it describes a good quantum state. So this means that this is a density matrix. You can verify that it applies to all the properties. So if there is a mistake, here there should be alpha prime, okay? It includes, it contains all the properties. Now, what is the meaning of that? The meaning of that is that, suppose the, so let me, first I give you the general definition. If from this small calculation, I show you that if I want to look only at physical observables which belong to the subsystem A, then even if the total state is pure, the state which is seen by the region, the subsystem A, will look like mixed. You can verify that if you compute the trace of rho A squared, this is less than 1. Now I will continue this tomorrow just to show you that this is another example in which, so let me make the following. The following example, okay? I'll come back to this tomorrow. So, let's consider 2 spin 1/2, okay? How can you write the most generic state of spin 1/2? Tell me. So it will be alpha up plus beta up down plus gamma down up plus delta down down. Right? Where, I mean, alpha squared plus beta squared, all this, they should obey some, should sum up to 1, okay? So this state is pure. Now, suppose the following. Suppose that I have these states. In principle, if I do repeated measurements, this is called tomography, but it's not really important. I can do several measurements in order to reconstruct the state, okay? So I just do measurements of the spin, of the spins in different directions, such that I can tell you what is the state. Now, suppose the following. But the measurements of the 2 spins are also, I mean, in order to have information about the spin, I really need also to have information about, for instance, sigma ZA, sigma ZB, and so on and so forth. So I need to know all these measurements. Now, suppose that for some reason I can only do measurements on one of the 2 spins. Then what I wrote so far implies that the system that I have will look like a mixed state. It does not like to be pure. So, don't worry. Tomorrow we'll finish our chapter on density metrics just by really considering this last part. The only thing I would like to ask you is to redo all these calculations so that tomorrow we verify if this is clear or not. Okay? And I don't remember who asked me a question about entropy and things like that. But tomorrow we will see how this connects to the entropy. Somebody asked me about entropies, no? The first lecture. Who? Okay, so tomorrow we will see. Good, so... just a moment. Question, do you prefer it this way or with the iPad? No, I want to know.
I prefer iPad because I cannot see clearly on YouTube.
Okay.
I don't know.
So just do the following. Just do a vote and you tell me what is the decision of the majority, because I cannot split myself in a quantum mechanical state, okay?
Yeah, you have was until
I don't know very well.
But I thought that professor intend to do somewhat in blur so that we have to do it ourselves.
Sorry, I did not understand. What did you say?
I mean, I thought that, I suppose that you intend in some part to make it not clear and then we have to do it ourselves.
No, I mean what you wrote isn't clear for me in the blackboard, not on this scale.
Okay, but
I think what Maha means is that when you write on the right side of the board, it will be clear.
It's really not clear.
Yeah, and usually the writing is also.
okay, so just a moment. So first of all, I understand, but then you should have told me at the beginning of the lectures, not at the end. Because, but then you have to tell me, should I stop here? Where should I stop writing?
Actually, before the line that is drawn.
Here?
No, I mean the line. You already see the line. There is already a line. But
This one?
you need to increase your font a little, so it won't bother them.
Yeah, but besides the font, my question is, do you prefer it this way or with the iPad?
I myself.
No, don't tell me now, because,
Yeah.
so how many of you are? You are 9 or 8?
I think we are 9 now.
Now, 9. So 9 is perfect. So it's an odd number, you can reach a majority.